Hello folks, this is another video tutorial on performing explicit dynamics calculation with the 3D Experience platform. Now, let me remind you that the native solver in the 3D Experience is actually the Abacus program. So this is perfect. This kind of tutorial is useful for people who are migrating from Abacus CAE to 3D Experience or entirely new in 3D Experience in the first place. Okay, so here's the situation. We are dealing with a rolling process. That means that, for example, a metal sheet block is pressed between two rotating drums, and that squishes the plate, and from the other end comes out a thinner plate. And one of the outcomes of this is, of course, uh, unidirectional uh, transformation of a steel block. So as you can see here, it is a relatively slow process, and that's why we call it quasi-static, in the sense that inertial terms are not important. Mass times acceleration is a small number. Acceleration is a very small number. Therefore, it's not really a dynamics problem. However, we will be using dynamics in order to uh, uh, perform a static calculation, and this is common, except that you may have to do certain tricks in order to make sure that the result come up in a reasonable time. This is a very simple problem, so you don't have to worry about too many tricks. Now, uh, typically, for example, 1 meter per second is the speed of the feeding of the panel, and uh, what we will do, because it's a slow process, we will do mass scaling. I will show you that mass scaling substantially increases the efficiency of doing this calculation on with finite elements. Okay, and it's not uncommon to have 40% reduction in a single pass, and maybe multiple passes, but anyway, ours is a single pass. So here's the the information taken from the resource down below. That a YouTuber has substantial uh, uh, videos on doing the same problem in the Abacus CAE, doing problem in Abacus CAE, and this particular problem was done or is done by the Abacus Acumen using the CAE program. The dimensions are here. Now, because this is drawing not to scale, obviously, and because of the symmetry of the problem, we don't have to model the entire process. We can model only 1/4 of it, and this is the side view of that 1/4 model. Now, the coefficient of friction is assumed to be point 0.3, and for actual rolling process, this number is very critical, but we will take it for granted that this is a good value. The other thing is that, generally speaking, the rotation of the drum, the speed of the drum, and the feed rate of the steel block must be the same, because you don't want to have you want to minimize the amount of slipping at this corner point, and therefore to make sure that this velocity is equal to velocity of the linear velocity of the rotation of the drum. Okay. Okay, so the cross section before it's being reduced is 40 millimeter by 40 millimeter, and total length is 92 inches, 92 millimeter. The material is assumed to be elastic, elastic plastic with this true stress plastic strain data, and we're using the properties of steel. So this is the density of the steel and Young's modulus, etc. Now, I will model the roller as an analytical rigid surface, which goes over that block, okay? Now, there's a couple of things I want to mention here, but I'll come to these later on, okay? So let me just quickly, this uh, formulation that the YouTube reference is using These are not, this kind of thing is not accessible directly to the user. Now, it is obviously possible to create an IMP file with 3D Experience and then go and include anything that is not put at the direct discretion of the user, but that's not what I'm doing. So, and the mass scaling factor is that this YouTuber is suggesting is 2,758 and factor of that. And I will try both of them, and I'll show you that if I do it with the mass scaling of this value, actually the thing runs in literally 3 seconds of wall clock. But if I do not use any mass scaling, it takes almost uh, what is that? 120 seconds. So that's about 40 times longer. Okay. Now you can imagine that if you're actually using a very complicated problem, that can make a big difference. Uh, and this is the details of the element size. When we do analytical rigid surface, you should be prepared to go, when you create it, to go and, if necessary, flip this direction. And in fact, I'll show you what happens if we don't, if we have the wrong direction. Okay. All right. So this is my model, and this is where I said that the YouTuber goes and asks for those things that one of them is not available to user in the 3D experience. Okay, let's go ahead and actually do this problem. The units are in tons, Newton, uh, millimeters, and seconds. Okay. Okay, I have created an assembly here. So let's insert our first part, which is going to be the block. Right click, uh, insert, uh, or or 3D part. And this, the first one is going to be the block. I can change the name and everything, but I'll just leave it the way it is. You know that the first part is actually the block. So let's go make it. Double click on 3D shape. And on that vertical plane, I'm going to sketch my uh, rectangle. Remember, we're doing a quarter model, so this is going to be 20 by 20. Let's dimension this thing, 20 by 20 millimeter, 20 mm by 20 mm. Exit, and we're going to pad it by 92 millimeters. Now I happen to be in generative shape design, so I'm going to go to part design. Although you can create solid a volume here, but I'm going to go to part design and do that. Okay. So under essential, there is a pad here, and I'm going to pad it by 92 millimeters. So that's basically what you see here. Okay. All right. So let's go ahead and apply material properties to this. We're going to go to tools, create material. I'm going to call this thing rolling process, rolling of block, and or pressing of the block. And this is November 6, 2023. And we say okay. Incidentally, I'm doing this thing on release 2023 X of 3D Experience. Okay, that's the one that I did. I'm going to apply. There's nothing in it. This is just a template right now. Let me refresh the screen here. Okay, right click, apply, I'm going to close that, apply it to this part, and green check mark, and now we're going to input our values. So double click. Because we're using explicit dynamics, uh, we need to specify the density. So structural, uh, general options, density, and I think it's 780, 7,800 kilogram per meter cube, which incidentally is 7.8 times e to the minus 9 uh, tons per millimeter cube. But I'll just leave it like this. And then we're going to go to abacus multiphysics, mechanical, elasticity, elastic. The Young's modulus of this was 150 GPa or 150,000 MPa, and Poisson ratio was, I believe, 0.34. Let's double check that. Zero point 0.4 actually, 0.4. So it's going to be 0.4. Okay, now plasticity, metal plasticity, plastic. Now here I have to input this stuff, this table, but I already have that in an Excel spreadsheet, so I'm going to import it. Okay, so right click, import, and on my thing in that desktop, already a rolling process, you say okay, and these are the numbers. Okay, there's 11 numbers, and that's pretty much it. So we say okay. Let's save this thing. I want to show you the Excel spreadsheet that I have, and I just imported it. It's over here. Let's see, somewhere here, right there. So I noticed that I started at the top left corner because when there were some extra rows and columns, it came back and complained. So that's how I did it. All right, so let's go back here. And now we're going to insert. Incidentally, the way I made it, later notice that it it this plane YZ plane is on this side. Okay, so just keep that in mind because this thing is important when you try to do symmetry, because later on I'm going to reflect this thing on the other side and the bottom, and I want to make sure that I can see it properly. Okay, let's go all the way to the top. Do a quick save, and then insert our next part, insert a new part, insert the 3D part, and this is going to be our analytical rigid surface. Okay, so what I'm going to do is first I will create a point. I will create a point here, which is 170 plus 15, 185 millimeter above that plane. That's going to be the reference point for that analytical rigid surface. So this, while we are at it, let's go to this first of all 3D part, the one that we are making now. And under essential, let's create a point and 185 millimeters. Okay, so it's right there. This is the reference point. Now, in that same plane, which is that plane, I will sketch that the arc, which eventually becomes part of the drum. Okay, so the pressing drum. So let me do let me do an arc. So the center is right here, and then I don't have to model the entire circle. It's not necessary because during the time that we're looking at, this does not make one full revolution anyways. Okay, let's dimension this. Let me see now. The radius of this drum is 170 millimeter right there. Notice that it's interfering, which is good because actually this block has to go through this. Okay. All right, so that's taking care of that, and And so this is going to be, I don't need the material on that because it's going to be an analytical ridge surface. Okay, so we go all the way to the top, all the way to the top, and let's do a save. And now we're going to move things around so that, oh, I forgot to actually extrude this thing. I forgot to extrude this thing because this is a drum, right? So that's just a cross section. Let's go back here. And in the generative, go to generative shape design because I want to create a surface. All right. And surface, there's an extrude. Where's the extrude icon? Right there. So I'm going to do maybe 20. Remember, this side is the symmetry plane, okay? So I'm going to extrude this thing further down, so maybe 30 millimeters. There we are, okay? Good. It doesn't hurt if you extruded that either, but it's not unnecessary. It's unnecessary, okay? So that takes care of this all the way to the top. And one more time, save. Let's anchor that analytical that surface right now. Let's anchor that. So you go to assembly. Here's the engineering connections, and we fix that uh, surface. Okay. Let me see now. You select that. You fix it. Okay. Good. So notice that this surface is fixed. Okay, and now we're going to move things around so that later on we can put this end in contact with that surface. Well, okay, so eventually I want to put this point on that surface. So why don't I just literally translate this thing right now so that it's easier for me to achieve what I want to. So this is manipulate. So I'm going to translate in the y direction. It looks like this. Okay. And now I'm going to put some constraints. For example, I want the bottom of this to be coincident with that plane so that this cannot lifted off the ground. So here's the connection, engineering connection to one user define, and I'm going to do coincident between the bottom of this and that plane. Okay, and of course there's nothing to update here because they were already or literally translated, so they're already at the same level. Okay, no problem there. Okay, let's try a connection between, uh, see now, user defined, yes, coincidence between, for example, let's see now, this point and that edge or that surface. There we are, and we say okay. Yep, that's fine. Good. There we are. Okay. So that takes care of, let's update everything by the way. Uh, that's okay because it is where it's supposed to be. So what we can do if needed, I mean, basically I wanted to put these things in place, and this is really not letting us proceed. That's okay. So we just going to delete that. It's in the right spot. Okay, good. Uh, Now, the rest of the problem is we have to go and create the mesh for this. So let's go ahead and just first of all, save everything all the way to the top, save everything. All right. And now we can go here, right click, insert a finite element or sorry, a representation. And for the representation, I can do insert finite element model. Okay, so I'm not going to go that route. I'm just going to go from here to structure model creation. That will automatically put it where you want to go. So MTFEM. I have gone the other route in some of the other tutorial. It says that there are two parts here. Which ones you want to participate? Both of them. Very good. Okay, so let's go ahead and actually mesh this thing. The information about the mesh is given here. 30, see now, 2.5 millimeter size. Okay, so let's go down there. So we go to mesh. We are going to be using a nice sweep mesh here. So this, uh, we can sweep this way or we can sweep that way. It really doesn't matter. 2.5, 2.5, and say okay. Very good. And close that. And then we're going to apply properties. So properties, solid properties. Uh, on the support is this object. And for picked up the correct material, and that's pretty much it. So this is it. It created the properties for us right on the top. You see that? Let's update. Make sure there are no issues. Good. Okay, so now we're going to do the analytical rigid surface. Now, the way to do that is you go to abstractions. Here, abstractions tab. Here is analytical rigid surface or rigid body. We're not doing a rigid body. I'm doing analytical rigid surface. You click on it, and it says, where's the surface? Well, the surface is at extrude, and says, where's the point? The reference point is up here. That's the point that I created up there. That is my reference point. Okay. There may be a need to go and flip this direction if things don't work out. That's one of the things that you're going to try. And if there is time, I'll come back and show you what happens if I did this thing or I didn't do it. We'll see. Okay, so that's good. So what I'm referring to, by the way, is that guy. All right, so the model has been created. So now we're going to go to this mechanical scenario creation, because that's the only place where we can do explicit dynamics. This one does not have the explicit dynamics option, but this one does. You click on it. All right, so we're doing a structural problem, and the finite element model, we just created it. Use the pull down menu, select the right one. There's only one here, of course. Okay. All right, it says there's no procedure, of course. So you go to procedures, you select explicit dynamics here, procedures tab, explicit dynamics, total duration of uh, 0.2 seconds, 0.2 seconds. I'm sure that was 0.2 seconds. They must have written it somewhere here. I don't think I've written it, but we'll do 0.2 seconds. So let's go back there. So 0.2 seconds. And then we say OK. All right. Now this point is, it can rotate about the x-axis. You can see that's the reference point for the analytical surface. So we're going to go to boundary conditions, applied fixed displacements. So this is the point. It can do everything except, it can do nothing except rotating about the x-axis. There we are. So that can rotate about the x-axis. Good. Now there's some planes of symmetry here, so let's go ahead and use it. So there's plane of symmetry, there's a plane of symmetry. So this bottom is a plane of symmetry. Okay. This side is a plane of symmetry. Okay. And now we have to give it velocities. So initial velocity, let's do it translation, apply translation of velocity. So that entire part, you can do it from the tree, or you can, select basically, let me do that. Right click, mesh visualization. Don't show me the mesh, just show me the part. So actually, it's not the face. Let me, it's the entire part. So it may be easier actually to do it from the tree. See now, where is it? Where is it? Right here. Part body. There. In the direction Y, so in the direction Y, 1000 is a 78. Let's see now. 1067.6. 1067.6. Don't forget it's mm underscore second millisecond. So it's going to become 1.067 or 68. That's good. So that's the initial. Ooh, wrong direction. Wrong direction. Direction Y. Yeah, that's better. There is an arrow here. If you can't see it, I'll show you how to fix it. Remember, you can go to Display tab. Under Display Operation, this Display option, you can drag this thing, make it bigger. There. See that? There's the arrow. That's why I didn't want it there. So let me put it back where it was. Okay, good. All right, you can change the transparency of this. You can probably see it also. Now, this is given a rotational velocity. This analytical rigid surface is given a rotational velocity. So we'll go back to uh, boundary conditions, applied rotational velocity, and it is that point, which is going to be our analytical rigid surface. If you're having a hard time picking it, you can either hide it or you can go and just select it from the tree, okay? Or you can select it from here. This is the analytical rigid surface. As soon as you do that, this point is going to be picked. Let's see. Oh, no, not actually. No, that's right. Apply rotational velocity. I'll do it from the tree or hide this and then I can pick it. Okay, that's better. It's about the x-axis and this is going to the right, so this drum must be also turning in that direction. And the value of it is 6 point, I believe, 6.28 rad per second. So 6.28 rad per second. Very good. What else? Oh, now we have to go and create interactions. So we go to interactions. First, we give it a coefficient of friction. So here's contact property with friction. Specify the value is 0.3. That's what we took. 0.3, yeah. 0.3. We say okay. And then we do a general contact. General contact, that's the easiest one. Because you can do surface to surface, but that's going to be picking a lot of stuff. General contact, but with the property that we just created. Remember, I just created the contact property 1. Otherwise, it's going to be frictionless. And of course, all surfaces are going to be involved. That's good. And hopefully, we haven't forgotten anything. So let's save everything. All right. Okay, one thing I forgot to do is to specify the mass scaling, and the place that that is done is right here while you are in procedures. If you go to the explicit dynamics that you created and expand this menu, it says mass scaling right there. And the value that I'm going to use to begin with, okay, I'm going to use now uh, 2000, what was that? 200758.5, 2758.5. That's the value of the mass scaling, and then the whole model, beginning of the step, you say okay. And let's just also check the type of element that I'm using. So if you go here, if you expand this thing, global element type, it's the reduced integration. That's exactly what I wanted, namely it was yeah, it was type of the element I indicated what I wanted. Yeah, right here, the C3D8R. The only thing I cannot do is to specify this because, as I said, it's not under user control, and unless you go and change the input file and then read it back and run it. Okay, so this is fine. Let's go back here, save everything, and run it. This will take roughly 3 seconds. Okay, so if you go to the simulate, first do a quick model check. When it, yeah, this is good. This is simulation check, and when it comes to running, you see that it will take roughly 3 seconds. Very fast. Of course, this is a simple problem, but I want to make a few comments about that. Okay, this is not the running stage yet. Okay, that was the check, and now this is the run. Okay, we're going to run it, and it'll take about 3 seconds. 3 seconds, yes. Here is the iteration, which shows you basically the monitoring window in the Abacus CAE program. There's the wall clock. Uh, Something didn't quite work. Let's see that structure failed. For more information, see the diagnostic viewer. So let's see what the issue is. Right click on diagnostic viewer. The ratio of deformation speed to wave speed. Okay, so here's what I'm going to suggest. Let's go to that analytical rigid surface. Remember abstraction? Double click on that. Remember I said be prepared to flip this? Flip it. Say OK. Let's go back to simulate. So scenario and run it. We can do a model check. No problem. Scenario check. A little bit longer. See? Okay, this is almost done. And now run it. Simulate. And this is where it bombed last time. So all I did was, the first thing I tried was to go to analytical rigid surface and flip the direction of that option that I had at the bottom of the dialog box in here. Okay, so let's check now, iteration, and we'll see how it goes. Yes, yes. This is the wall clock, and it's going to finish in did I say 3 seconds? It took longer than that. I guess it depends. Okay, so let me close that and let's look at what happened here. You see? Okay, so this uh, duration was probably too much. Okay, so that total duration was too much, and this is why it took longer than what I wanted. So actually, I go here. Let's go back to that here, explicit step. That's the one that I wanted. Let's make it actually 0.02 seconds because I thought it was 0.2 seconds, but I may be wrong. Let's run it again. I couldn't remember what the duration, time duration was for the reference that I'm using. I thought it was 0.2, but may have been a different number. Remember that has nothing to do with that check mark that we put. We flip the directions. That's more like when you have when you're doing surface to surface. If it's not the correct direction of the surface, of course things are going to go nuts. Yeah. So here you can see the iterations. This is the one that, let's see how many seconds this took. Yeah, right here, wall clock 3, right there. Okay, so the other one, the duration was so much that actually the whole thing flipped. And okay, so let's close that. Okay, so you can see this. So this is the last step. This is the, okay, and then you can animate it right there. Okay, so you can see what happens. I may want to extend this thing. I can extend this thing, maybe that I can't even remember whether it was zero point 0.2 or 0.02. It could be that you have to go, it could have been zero point 0.2, I'm not sure. But then that if that is the case, then you have to make this uh, uh, analytical ridge surface longer in one direction. Okay. Now, a couple of things I want to show you. Let's exit that. Display results option, not display option. Results option under the display tab. Under the display tab, results option, and then you say you click on this icon, model symmetry, and then model symmetry. Check that box, and then say reflected with respect to XY. Okay, that's good. And with respect to YZ, yeah, or YX. So the whole thing is faked to look like the model before symmetry. There we are. Okay, couple of comments here. Number one, we are using a lot of mass scaling, factor of 2000. That accelerates the process as far as computation goes. But it could also lead to unrealistic results due to hourglass control and things like that, hourglassing and things like that. So let me show you what happens if I go and eliminate that mass scaling from the factor of 2000 to a factor of 1. So we go here under explicit dynamics. Where is that thing? Explicit. There is a mass scaling, right here, mass scaling. And I'm going to change this thing from mass scaling of 2000 whatever. I just put down 1. Essentially means no mass scaling. And then run it again. When I run this thing, you will see that it takes longer. This will take about 3 minutes. So let me go ahead. I'm not going to check it. And I will stop the video right here. And when it finishes, then after 3 minutes, we will come and look at that. Okay? Okay, I'm back recording, and notice that it took roughly, here it took, in this round, it took about 46 seconds. So let me close that, animate it. Now, this took longer, but there is no danger of, there is less danger of that mass scaling coming into the picture. Uh, the takeaway from this tutorial is that be careful. There may be a need to do that. Depending on how I model this thing, it could be that it would have gone through, okay? And that's pretty much it. And the fact that this is not directly available to the user in 3D experience, you could, as I said, you can always do that by going to a log file or INP file, not log file, INP file, make changes there. But that's pretty much it. Good luck.